Okay, and we should be as live as it gets now, right? So that will be on the channel website. So whatever is there now stays forever on the internet, which is fine, right? So today we want to calculate the hydrogen atom in NWChem, and we want to see if we can plot some orbitals. We want to see if we find the total energy. We want to check if we actually can uh, succeed in performing a calculation, if the calculation has any meaningful values for us. So this is big enough for you here, right? Right? So NWChem is a quantum chemistry software. It has become very, very nice in recent years. Let's see here, NWChem main page. I actually like the GitHub page a little bit more. Right, so it's an open source, high performance computational chemistry package for biomolecules, ground state and excited state calculations. We can use our Gaussian type basis function or plane waves. It's a lot of possible. The documentation is extensive. There are a lot of examples. For us, most important would be, for example, basis sets. If we click here, then there's a documentation how to use the basis sets. We can go to geometries because we will need to define the atomic structures. Scroll down, there's a lot of things we can choose from. There should be examples as well. And then here, NWChem examples. Sample input files. And they give you here the example for water. So far, so good? Okay. So what you could do is just copy this, plug into, I tell you, right, you could copy, I can copy as well. Then I go to my work folder. Last time we said you must be in your work folder to perform calculations. And then I would make a directory, water, H2O water, Vim, ground state dot, I normally would call it NW for NWChem, and I for input. I push I, then right click, paste, white space. There's my input, okay? So how do I know this is water? You must carefully see the, this is not clearly. Okay. Well, so let's see what the input has. There's a start with a name, water, right? Okay, then there's a title, water in 631G basis set. It's a string, right? You see the quotation. Geometry, units, atomic. Okay, so we have oxygen at position 000, X, Y, and Z. Okay, so we have some coordinate system like this room. Let's say I say 0 is over here. I put oxygen there. And then X0, Y 1.43 and minus, and Z minus 1.1. So 0, and then I go 1.4 units Y and up Z, right? And for the other hydrogen atom, I go minus Y and well, up or down, depends on the orientation of the Z, right? But it looks a little bit like water already, right? With oxygen in the middle, and then a little bit upwards to the sides are hydrogens. So this is geometry, and then it follows an end. Right? That means your geometry definition ends here. The program knows I read atoms until end, and then I start reading atoms. And then I start writing down my bases. Hydrogen used from the library, so NWChem comes with some library of basis functions. So you don't need to go to that website I showed you earlier with hydrogen and 631P or single type. You just write what you want to have. Okay? And then oxygen the same. And so the basis block has been finished. And then you write task SCF. SCF is self-consistent field. After we have performed the calculation, after we have checked the calculation, I will tell you what is the self-consistent field. So far, so good? So you have this already?
No?
You want to
I
try?
have a trouble because my connection is refused.
Then you must use the VPN of the school, right?
I hear I need to use a VPN.
No, if you're here, then you should be just able to log in the school website.
Yes, I connect the school website. The internet and the connection refused.
You two log in already?
I will be logging to the computer.
Why is your connection refused?
I don't know.
Did you put in the password 3 times wrong?
Yeah, yes, it's ready. Yes, yes.
Then you locked the server for today.
Okay. Okay. See you tomorrow. You have a video?
I have a video, yeah, this is recording on
Okay, I see.
on your video.
Okay.
So you copy this and you make a file, right?
Yeah, okay.
I have a question.
Yes.
The file
Yeah.
we should find from the best that it can.
No. From NWChem. NWChem examples, sample input file. So here's the thing, right? So I expected there will be some, it's normally difficult to get started. So what I did is I also made us a shared work folder, AMD. AA 2024. That should be a shared folder. Permission denied. That's interesting. So let's see. Okay, so I put it now into the shared folder. So when you go here, right, work AMD 2024 shared, you can copy this file into your wherever you are. So what you can do is copy from work AMD 2024 shared ground state of water, and then I'm in my water folder already. I put push, right? Just the dot. The dot means like the destination, and destination dot means where I am right now. And I am in my water folder. So I have the file here. So far so good. And always remember, be in your work folder to do calculations. Now, what else do I have? I have a submission step. Last time I told you we need to submit to the queuing system to perform the calculations. Do not use the login node. The login node is the computer we log into. I showed you that. Yes. Okay. So I copy now my submission script to the same folder. Okay. So let's look into the submission script. Looks like this. It's quite simple. It uses a slurm, right, in the S-batch interpretation, flavor, whatever, right? So there's S-batch and there's QSUB. I use PBS, right? I use S-batch. Job name is called NWChem. We are using the partition AMV 2023. So this is the same dedicated compute node that I set up for the course last year. We use one node because the whole partition is just one node. One node is one of the racks we pulled out last time. On this rack, we asked for one core. So we're not using all the cores because we have just a small calculation. So we just used one core. And then we say, do not use OpenMP threads or set them to 1. And so OpenMP threads is normally set to a certain value. Is that we don't need this. We don't need this kind of parallelization here. Set it to 1. Then we get the present work directory. We get the username. Who am I? It will tell you your username. And then you say, hey, we store the value that we pass as argument to the script. $1, we store that in bold, and then we call NWChem on the compute node. This is then not executed anymore on your login node, on the compute. We pass input file and we write as the output file. And at the end, we are removing any temporary folder. Okay? You must be careful. NWChem writes a lot of files, big files. So you will run out of your quota of 10 gigabytes pretty much soon. So far, so good? Yes? Why not?
I don't know how to copy the file to any
So this one, no, you need to copy ground state. So type exactly this one.
and the NW1 I should
I.
change I.
No, did you?
I.
It's I.
Yes, this is back once.
Can't see anything anymore, right? A bit too large, maybe. NWI, right? Okay, and then very easy, we do S-batch. The name, wherever you copy your submission script, you need to find it. 2 dots means I go one folder up because my submission script is not in water, it's in this folder. Right? You need to copy the submission script from the shared folder somewhere. You can copy it anywhere you like. My submission script is not in the water folder, it's in the folder here. So when I call the submission script with sbatch, that is the command to tell, hey, I have a file for the Slurm queue manager, the submission script, because I want to perform a calculation. Then I need to give the path to that file. But the path is one folder up, right, in the folder structure. It's not in water, it's here. So I take 2 dots to say this file is in the folder up. I show you again. So when I look into tree, you will see the folder structure. Right, I already done some calculations here. So tree calls where am I? And then I have 1, 2, 3, 4 few folders, right? In the H folder, I have nothing. In H2, I have a few files. In H2O, I have the ground state file. You see that? Right? But then I'm looking for my submission script. Where is it? Where is it? Where? It's the very end, right? Because and in my current folder, the line goes down over here. So this is where my submission script is, right? So when I go now one folder down into H2O, right? I cd, I change directory in H2O. Then my submission file is one folder up. I need to go one folder up, find the file. Again, I know where the file is, so I can use the file as the s-batch submit. But this script requires one argument, right? The value we store in mole to pass to NWChem, and that is the file I copied just now, right? The information for NWChem, which calculation to perform. Do I have water? Do I have CO2? Do I have a macro cycle? Do I want which basis set, which functional? I don't know. Also good? And when I have this, I push enter, okay? That will tell you your job has been submitted and this is the job ID. Good, and then I can look for the job and let's do a little bit smaller. You see the job ID, right? Matches. This is the queue, in the right queue. This is the job name, that is my username. PD means pending, meaning something is busy, right? So we need to wait until it's our turn. And this is how many seconds or minutes the calculation is running already. It's running. Now, you see, it's running already on this node. Right? So if there's a trouble with the node because the CPU breaks or whatever, I can find the node. And it's running for 19 seconds already. That's okay, done. Now you try.
So this computer is locked for today?
The server is locked for today.
For my user?
For everybody. So the moment you log out, you need to wait until tomorrow before you can log in again. It's okay. It's a safe. For everybody, yeah. No, for everybody. Because, I mean, you always can change the person quickly if you really know what you do and then try again to log in, right? No, it's fine. If we are under attack, I basically shut down everything because nobody wants to wait these days. So what they do is they look for the next target, right?
I still can see the folder.
Yeah, because you're currently logged in, right? But the moment you log out, I shut down. Basically, you cannot log in again for 24 hours, right? Nobody can.
24 hours or
24 hours. It's okay. Patience. Patient, you can go to the beach, can meet your friends, can read something. Right? I give you a paper to read, very nice one, right? And you should also read that paper, by the way. The molecular cartography or something like this, right? It's really nice, I think. Okay, so so what I can do is, I can see how busy the queue is with watch. Nobody uses the queue. Did you submit your calculation already? Did you succeed? So if you succeed, you should see an output file. If it's failed, then something went wrong, right? So you must figure out, you should see a slurm file. So there are two things. One is from the scheduler, who's responsible that your calculation is submitted and collected. And the other one is your calculation itself. So if your calculation succeeds, right, you find the output file. It's one of the signs that your calculation succeeded. We still need to check if it really succeeded. But if something failed or you don't see your output file, you check your Slurm file. And it tells you, oh, there's a warning, some feed one leaked allocations, okay, some memory leak. It's okay, it happens. Cannot remove 10 because this is meant for something else, but it's okay. There's no big error message here. How about you? What do you get?
It's the color of the area.
Did you use my submission script?
Yeah. It failed to open the input file.
Then, because when you submit, it's very good that you already read the error message, right? But sometimes you need to read the error message properly. It will give you a lot of information. If you run the script correctly, the first argument here, right, for the script is the input file. Right? So the command itself has two arguments, the submission script and the input file. Because the input file is used as argument in the submission script.
Okay.
So in the bash language, you see this $1. That means this is the first argument that's being submitted. Right? If I have two arguments, we can do this, alright? We can always have the second argument, echo, second argument, okay? And then we submit again. Let's see, dispatch, my second calculation. This is the second argument I give to the script. Then I do watch again to see how my calculations are doing. So I see user 3 is running a calculation for 20 seconds, done. So somebody should have an output file now. Mine is still pending. You should be able to run a few calculations at the same time. But the scheduler is very busy at the moment. It takes a little bit of time for it to pick up and handle new calculations. Still waiting. So do you now get an output file? Yeah. Very good. So it's running now, right? Vivian, how's it going for you?
This class is after the video on the web,
It's
on the YouTube, all the video, or just part of it.
This is now streaming live, everything. Right, so if you go to the channel and the live stream, you see everything, and everybody who logs in will see it as well. Right. But
Part of it, so I didn't connect to this class.
I don't really understand.
我没有看完全部的影片，真的。
Your video you up last week you upload 4 videos, just talk about download some software and the common CD something talk about something like so it's not related to this.
It is related because we CD all the time, right?
Yeah.
And we copy all the time.
Yeah.
So we're using Linux, right?
Because we say, oh, I didn't finish the video, so I not necessary to
Understand.
It's okay. The video. It's okay. It's okay. Then you watch them later. I don't know.
Okay.
You don't. So the important thing is you need to navigate the Linux OS, right? So when you know what CD is doing and LS and whatever, you're fine, right? And in principle, if you follow the steps I do here, right, you should be fine as well.
Maybe I already understand slowly.
Yes, it's okay, right? So, but you need to. This is the skill-based part, right? So there's knowledge-based part and skill-based part of lectures, right? This is skill-based because we really do something. Now we are going to check. Well, let me bring is a calculation, yes or no?
Yes.
So let's see. Input file is directed. This is a directed. Application, this is a directed. Substrate is the copy into your workflow. So because kind of the run calculation.
Already. I new folder in here. Should in the folder.
You should CD into your work folder, right? And then if you CD and put the working directory, you are and then you folder for something like CAM or for local, right? CD into local, copy the file share folder. This one, submission stuff. New, search, submission stuff, file name. Good. So anyhow, so we were at the second argument in the submission script, right? So let's check what we did here. Right? Because I echo now the second argument, I see my second calculation, the second argument. So I can add more and more arguments in the submission script, just use them smarter. Let's see, watch. So your calculation is still pending, right, which is okay. But when it is done, so to check your calculation pending, you type SQ, vertical line, grep, AAND. Let's also check my Q. You can also try check my Q. But my queue is a little bit full. So I do the graph thing to just show you the queue we have in common, right? Okay, your calculation is running. It should be finished soon, and then you can go ground state dot out. Okay. And this is what we see. This is the output file. So what it should tell you, for your input file was ground state NW in, right? And then the program starts, right? And somebody decided to say, hey, the first thing in your program is what program are you using? So Northwest Computational Chemistry Package, NWChem 702. And then you see where it's from, Pacific Northwest National Laboratory, copyright, NWChem is an open source. That means free to use, free to modify, but you need to acknowledge. Computational chemistry package distributed under the terms of ECL 2.0 and educational community. So it's right where we belong. Acknowledgement, the software, the documentation will develop at the EMSL. Have you seen this today? Right, that's where we looked at the basis. Okay. Multi-program national laboratory operated by the US Department of Energy. Yes. So when we publish something with NWChem, we should acknowledge that we used NWChem. Good. So So we have a few job information, hostname, that is the node, which is the program, that's when the calculation started. This is when NWChem was compiled, the version, that's Scala file used, but we only use one CPU, this is one core actually, right, one core. That's okay, so then memory information also, so we have allocations for like 100 to 400 megabytes. This is enough for small calculations. If we go bigger, right, we need to tell NWChem, please ask for more memory. We can do this, but in this course we will not need this optimally. This is important. Your permanent and your scratch directories, the dot means where the calculation is at the moment. That means big files will be written in your folder. You will run out of quota pretty quickly, so later we will replace these folders with the temporary folders of the compute nodes. Okay? Okay, keep your data clean. Then what do we have? This one, the title we gave the calculation in the input file. Remember? If you don't remember, open the input file. So far so good? Input? Yeah? And then water has water is which point group? Point group, Schönflies notation. There are symmetries, right? And symmetry has point groups and space groups. Point groups are normally for, let's call it localized objects. And then we have different symmetry operations, rotations, mirroring, inversion. And water is quite symmetric, right? So yes, exactly, which point group belongs water to in Schönflies notation?
Okay.
C2V.
C2V?
Right, it has a C2 axis and a vertical mirror plane. Through oxygen, right? And the C2 axis, so you rotate water 160 degrees, 180 degrees, right? Looks the same. And you do that twice, you're back to original, so C2. If you have some 4 points, you need 4 rotations, right, to go back.
Okay.
It would be C4, but water is C2V, and NWChem detects that symmetry. Okay? Good. No constraints. We want a geometry. The geometry comes next. Here we have oxygen, recognized to have 8 electrons. Position. Hydrogen, recognized 1 electron. Position, and another hydrogen, another position. Now you see, these positions are slightly different.
Yeah.
Right, so they are shifted already, and it should be through the gravimetric center. So it looks, if you take oxygen and you put it on a plane, right, where do you need to put the stick to balance that oxygen, right? That is the gravimetric center. Did you do this as a kid? If you take something, you put something on a stick, and then you try to balance it, so that is the gravimetric center. You can calculate this, right? Yes. Oh, I'm not using the right microphone, I just see, because I never plugged this in. That's okay. So now it is in. I'm not sure if it is, so the audio signal will be pretty bad. Yeah, it's students rightfully complain about the audio quality, right? But it's pretty hard to have decent audio quality with the means available. Anyhow, so they shifted it so they also can detect the symmetry. Atomic masses taken here, right? So this is the proper values already. Effective nuclear repulsion energy, right? So this is your potential between the atomic cores. Nuclear repulsion energy, it's repulsion because they're all positive. right? And nuclear means the atomic cores. So far, so good. Then we have some information about the symmetry again, which is all right. Then we have, information, nuclear distances, more information, bases. So here we see the bases, okay? So when you go back to your EMSL website and you look for 631G hydrogen in the NWChem format, it gives you the numbers, and here it's written now, exponent and coefficient. Right, so now we know which is zeta, right? Which is the exponent and which one is the coefficient in front. So in principle, you can take this now Gaussian type orbital, 631G, G is Gaussian. You take this, you do the proper contraction, and you should be able to represent a similar wave function as for the hydrogen atom.
So we can put this into our function.
You should be, yeah,
Okay,
yeah.
okay.
And then we have the same for oxygen, but oxygen has much more, right?
Yeah.
Okay. P, S, P, and now 1, 2, 3, 4, 5. Okay. Okay, what else do we do? Then we have summary of atomic bases. So we have how many bases, function, and types? 2, 2s, right? Because we have 2 shells here, 6 and 31. And 5, 9 functions, type 3s, 2p. And then the NWChem self-consistent field module starts. So we take the atomic gases of the electronic states and now optimize them to represent water. So we start trying to minimize some energy, finding the density and wave functions for water. So we have a lot of information again. So the calculation, the wave function we do as restricted Hartree-Fock, not DFT. Right? Anyhow, so we do later. Okay, then we go on. We should find some total energy values, yeah, the sum of the atomic energies. So we take the atoms, we look atom for atom. What is the energy of each atom? Sum them up. We get this one. That's the starting point. If we do our job right, we get an energy smaller than this. Non-variational initial energy, right? So we put them now the atoms together, and they already start to have some kind of benefit in being together, right? So the energy is already a little bit smaller. And then we see the 1 electron contributions, 2 electron contributions, and an estimate for the HOMO and LUMO energy. So 2 electron contributions are electron-electron interactions, right? Good. So what else? And 1 electron, by the way, is, for example, electron-core interaction. That's why it's negative, binding. Kinetic energy would be always positive, of course. Good. So what do we do? So a lot of information, restricted. Okay. So here. So we have a gas of the density, right? From the atoms. We plug this into our energy formula. We get this value. Remember, 75, 94, 73. 74, 90, already lower, very good. Okay, and then we say what is the time spent, it's pretty quickly, and then we get a new wave function, okay, because we try to optimize some of the coefficients for the external potential given by the cores. So in our second try, we take the new wave function, we get the energy, right? And we see, hey, this is lower. This is lower by how much? What's the unit? What's the unit? We figure that out later when we just look into the hydrogen atom, right? The important part now is, right, we do it these updates of the wave function density another time and another time, and you see that the differences become smaller and smaller. that means I do a calculation over and over again, and it's getting better and better, right? And at the end, the differences are like in 1, 2, 3, 4, 5, 6, 7 digits behind the leading order, right? So this is like 8 digits here, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9 digits. So normally, then let's say 9 digits is as good as this bad. It's okay. Remember last time you saw an energy, a difference 9 orders of magnitude. Right? Is 9 orders of magnitude large or small? How large is 9 orders of magnitude difference? 10 to the power of 9. Like if I would be 10 to the power of 9 times smaller, right? Then it would be roughly the size of an atom. A little bit larger, right? If I had 10 to the power of 9 times more money on my bank account, I'm not sure if I would be here today. Yeah. Right? Probably I would be here, right? But maybe not after 12. Okay, so and then, right, so it tells you at the end, final restricted Hartree-Fock result, I minimize the energy, right? So now I'm really low in energy, and I think that is the correct energy. My 1 electron energies are these values, 2 electron energies are these values, nuclear repulsion, this contribution. If you sum them up, what you get? Do you get this one? You can try.
1 plus 2 and a plus.
This plus this plus this is this?
Okay.
I don't know. You do the check at home, okay? Okay, so what else? And then it will tell you, oh, I have orbitals, and the orbitals have some symmetry, right? A1, A1, B1. We saw that today in the discussion of the, very, very briefly in the discussion of the d orbitals, right? So this is the symmetry part. Then we have eigenvalues. This is very important. Eigenvalues are our orbital energies. Okay. Normally, we would have bond electrons, which are below 0, right? How many electrons do we have? We have 2 from the 2 hydrogens, and oxygen is how many? Oxygen has 8 electrons, right? So 2 plus 8 is how much? 10. How many binding orbitals do we have in water? According to this calculation. Eigenvalues, each orbital has 1 eigenvalue. So we have 5 that are negative. So 5 are binding, right, or bond states. We have 10 electrons, so we can fit all the electrons in here. So no electron will fly away, right? Plus, it's very unlikely to fill an orbital, right? Because it's higher than 0. Anyhow, there's more to it, right? But this is the basic idea. And then the difference between occupied and unoccupied. I know which is occupied because I know the number of electrons. I use the Aufbau principle to fill my orbitals. I have 10 electrons, so I fill until here. Occupied, unoccupied. So this one is the highest occupied molecular orbital, minus 0.5014. And the lowest unoccupied molecular orbital is orbital 6, 0.2038. Energy difference is obvious, right? We just need to check the units. Good. Then we have a summary of the orbitals, and then we see basically what are the coefficients in the optimized functions based on our bases, right? So now we can take the basis of each atom. For example, atom 1, function S, multiplied with this one, add the other oxygen here, right? And that will be our main contributions to that orbital. So we can take the basis, these numbers, and then print our orbital, right? And we know which orbital it is because it tells you vector 2, this is the second orbital, occupation is 2, this is the energy. -13563, -13564, right? 3, 4, should be rounding, right? Rounding, yeah. And then the next one, so we go to orbital 5, which is our HOMO, occupation 2, this is the energy, and we see, this is a p orbital, py, right? And the other one here is also a py. Very good, so we have py's, and my LUMO is unoccupied, occupation is 0. Right? This is the energy again, so energy matches to the orbitals we saw earlier. And then we see S character, P character, S and P character, so the SP hybridized state. So far, so good?
So P have the different like PY,
Exactly, PY, PZ. PZ, PY, correct. Okay? So later, at a later stage, we will basically make a file so that we can look visually into the orbitals or at the orbitals. But you always need to check that what you did is correct, because whatever can go wrong will go wrong. You need to be able to figure out if you did a mistake, if the program is working properly, that everything is correct. So you have a lot of information, right? And if you, for example, your HOMO orbital looks like a spherical, right? Like a ball. But it says here PY orbital. Then something doesn't match because a P orbital looks like a dumbbell, right? So something is funny, right? Would be funny. So you need to always check and check and check. And there are a lot of ways to check. You need to know them, you need to apply them, and then whatever you present to your best efforts must be correct. Good. We go down. I'm talking too much and too slow, right? Because I have to leave soon for the teaching survey. Remember, we have the teaching survey in 5 minutes.
Yeah, 5 minutes.
Right. And at the end of the calculation, they tell you, please cite the following reference. And you see a lot of people have contributed to NWChem, right? Because it's a really, really nice program. It's open source. You don't have to pay for it. It's available for everybody, even you at home after you leave university. And you're like, hey, I really want to compute water again. You can come back here, install it on your Ubuntu or Linux, maybe even Windows, and then just run these calculations. More things, so there are 2 references, I think. No, okay. Good. Wall time 20 seconds, computing time super fast. But the network, I think, is pretty slow. Good. Now, what do we do? We change a little bit. So I go here for my other example, edit, because I really want to do a DFT calculation with you. So I copy here something, and then we modify our input file, ground state. We can actually copy ground state to DFT ground state.nwin, right? And then DFT ground state. We have here a basis. For DFT, I must specify in NWChem a little bit more. I think I don't need the title. I write DFT. Okay. Then I write XC B3lib. It's actually hybrid functional. Multiplicity. For water, no unoccupied orbitals, I write 1. I write end to end my DFT block. So this is NWChem typical. I start something, I add details, and when this context of information is finished, I write end. Then I write task DFT energy, not SCF. I can delete this. So far, so good. Then I SBatch my submission script, DFT ground state. Not sure if this will work because I changed something, right? Some text. Watch. So now we wait until it's changed, but I'm basically changed now the input and say, hey, instead of doing a Hartree-Fock calculation, please perform a DFT calculation with B3lib. Pretty easy, right? You didn't need to solve any integral. You didn't need to write down any basis function, right? You didn't need to compute any density. Just a few details, right? Push some buttons, find the total energy, we saw that, and you're done. What else, right? So calculations can run in parallel. Right. So what you can do already is put any other system in a Hartree-Fock calculation and compute their total energy and compute their orbital energies. So instead of water, you could take sodium chloride molecule, right? You could CO2. You can take CO, ammonia, whatever, and get the orbitals, right? Get the HOMO-LUMO gap in Hartree-Fock. So apparently now it is 1:50, the calculation finished. You know what to do. I have